This is the pre-lab for the photoelectric effect. We discussed this in the lecture. The laboratory itself is fairly straightforward to carry out. The instrumentation automates most of the tasks. The basic idea: shine light on a material. Light often indicated by the energy for a photon, h nu, and you eject electrons. These electrons come off with some kinetic energy. And Einstein showed that by conservation of energy, the kinetic energy was equal to the light of the photon minus the work function, the energy with which the electron is held in the material. So the setup is to shine light on the material. Electrons are ejected, and you have a plate, an electrode that measures the current, essentially between that and ground. So the electrons are ejected and they flow to this, and then you change the voltage on this plate until the electrons no longer reach the plate. So the voltage, you make it a negative voltage, and you step that voltage up until the current is 0. At that point, you have the potential energy across this gap equal to the kinetic energy electrons coming off. So you get the charge on the electron times the voltage is equal to kinetic energy, which is equal to the energy of the photon minus the work function. So this is known as the stopping voltage, the voltage at which no more electron current reaches the material, or sorry, the electrode. So the instrument that you'll use determines this automatically. There's just a little multimeter connected to it, and it measures this automatically. So you'll measure the stopping voltage versus frequency of light. I'll talk about that in a second. So analysis of this is fairly straightforward. If you just divide both sides by E, which is the charge on the electron, you get the stopping voltage is Planck's constant over the charge on the electron times the frequency minus stopping voltage over the charge on the electron. So this suggests that a graph of stopping voltage versus frequency should have a line whose slope is Planck's constant divided by the charge on the electron, and then the intercept is minus the work function divided by the charge on the electron. So knowing the charge on the electron, you can get that from the constants in your book. You can figure out from this analysis the slope, which will give you Planck's constant. So you calculate Planck's constant with this, and then you'll also calculate the work function of the material, and in the lab report we'll exercise try to identify that. So the last issue is how to measure the frequency of the lines. That's fairly straightforward. You use a mercury emission lamp. So it's giving off light. It goes through a diffraction grating which disperses the light into the constituent colors. So what you'll get is you'll get a band of light in the center, which is essentially the non-diffracted light. And then you'll get purple, green, and yellow lines off to the side, kind of in a circle. So you get purple, green, yellow. And so this is first order diffraction. And these will be spaced fairly closely together. And then out here you'll get lines purple, green, yellow, the second order. And likewise here, purple, green, yellow, second order. And so it has the device, the instrument has a little detector that has a pin here so it can swivel, and you can shine it so that each line is shining on the entrance slit to that. There are filters for the green and yellow to filter out, because the green and yellow are pretty close, to filter out green and or yellow to make sure those aren't interfering. And then the device will automatically read the stopping voltage. So you just have to put it on the appropriate color line and measure the stopping voltage for each of those. And then you can average, right? So for all the purple lines that you measure, you'll average the stopping voltage, and likewise for the green. The mercury emission lines are well known, so you can look online in reference sources and find the wavelengths of the purple, green, and yellow emission lines, and then you can convert wavelength to frequency, and that will allow you to calculate or determine the frequency for the analysis for the experiment.